I will demo the PCLH memory process file system, which I use to find Total Meltdown with. And I will also demo how I came to find Total Meltdown and how I came to believe it to be already fixed and how I then released it into the public without it being fixed. And throughout the presentation, I will do demos, lots of demos, live demos, so let's hope everything is working. My name is Frisk. I'm working as a pen tester by day here in Stockholm in the financial sector. I try to do some security research by night, mostly DMA-related stuff. I previously presented here at SecT, and I'm also the author of the PCLH Direct Memory Access Attack Toolkit, which is a 100% open source project. I have to point out that I'm giving this talk as an individual. My employer is not involved in any way. I'm here today to present Total Meltdown. It's a local privilege escalation vulnerability. It allowed any low-privileged user to execute code in the kernel trivially. It was way worse than the original Meltdown vulnerability. Total Meltdown allowed for arbitrary memory reads and writes at speeds up to gigabytes per second. It only affected Windows 7 and 2008 R2. No other operating systems were affected. It's not directly related to Meltdown. It's not a CPU or side channel attack. It was rather a bug in the Meltdown patch, which was rolled out in January, which then opened a backdoor straight into the physical memory of the computer. And me releasing this one, it resulted in an out-of-band kernel patch from Microsoft 2 days later on March the 29th. And immediately when I released this one into the public, even before anyone knew it was a 0-day, it got like huge media attention, and some of the headlines were like, Meltdown fixes from January and February made PCs more insecure. So let's have a look what we can do with this one. Let's dump the entire physical memory of the target system. Let's insert some evil kernel implants, execute code in the kernel, and let's elevate the system. So here I have a Windows 7 vulnerable virtual machine with the January patches. And as we can see here, I'm not cheating here. I'm not admin since I'm prompted for a password here. So if we try to dump the memory, we are dumping the memory at a few hundred megabytes per second here, and this is because we are running in a kind of slow virtual machine here. If you're running on real iron hardware, it's usually a lot faster. We're also able to execute code in the kernel, and this is the same kind of PCLH kernel modules that I previously demoed here at SecT in the previous years. So now we have kernel code execution as a normal user. It's also rather easy to elevate the system and check who we are, just clicking on a file like that. And I mean, this is not supposed to be able to happen as a normal user, to be able to do this in Windows 7 or 2008 R2. So what is going on here? And that's what I tried to explain in this presentation. But first, let's have a look at Meltdown. It was a CPU bug. It only affected Intel CPUs. It was called Meltdown because it melted security boundaries, which were normally enforced by the hardware. It allowed low-privileged processes to disclose, that means read, privileged virtual memory, such as kernel memory, if it was residing within the same page table hierarchy as the low-privileged code that was trying to read the privileged memory. And you could do this up to speeds around 500 kilobytes per second under very optimal circumstances. Meltdown was independently discovered by 3 teams back in 2017, and it led to a coordinated disclosure and patch releases from operating system vendors in January 2018, this year. In order to be able to understand what's going on with the demo we saw earlier on, we need to have a look how paging works in a modern-day computer, how 64-bit paging works. Memory in a computer, it's physical. And the physical address space, you have one physical address space, which ranges from the address 0 to approximately the amount of RAM you do have in the system. CPU cores, however, they execute their code and work on their data with virtual addresses. And you have one virtual address space per process in the system. A user mode address looks something like this, and a kernel address looks something like this. A kernel address traditionally starts with 4 Fs. And what's going on here is that you have a CPU core or CPU cores that is executing code and doing stuff with their data. And in between the CPU core and the main memory, you do have a memory management unit, which is translating pages of memory. That's what it's called paging, and a page is 4 kilobyte page-sized chunk of memory. And it's transparently translating the virtual memory into physical memory. And in order to be able to do this, it has some lookup tables, which are called page tables, which are also 4 kilobyte sized page sized. If you take a virtual address, for example, this one, we can display it in binary. We can divide it into different sections. The topmost 16 bits are just a sign extension of bit 47. So it's always the same as bit 47. So if bit 47 is 0, all these bits are 0. Otherwise, they're 1 if bit 47 is 1. So in reality, we do only have a 48-bit virtual address space. The 12 lowest bits in the virtual address are used to address within this 4 kilobyte page that I was talking about earlier on, to address on a byte level. The topmost 9 significant bits is the index of a page table entry, or rather a PML4 entry, in the topmost paging level in the paging hierarchy, also called the page mapping level 4 at level 4. And in this case, it's index 493 or 1ED hex. The following 9 bits are the index in the level 3 paging table in the paging hierarchy, also called the page director pointer table. The following 9 bits are the index in the level 2 level in the paging hierarchy, also called the page directory. And the following 9 bits are the index in the actual page table itself. You have a PML4 at the very top, at the 4th level in the paging hierarchy, and every paging table has 512 entries, 8 byte each, or 64 bits each. And the base of the PML4 is located by the CPU or the memory management unit by the CR3 register in the CPU, which contains the physical address of the base of the PML4. The PML4 is traditionally split into 2 parts, while the lower part is reserved for user mode code, while the upper part is reserved for kernel code. And if we look at a page table entry, they might be blank here, or they might point to different levels in the paging hierarchy after this. But if you look at the random entry, for example, this one, we have some bits in red here, which are usually permission bits. And if you read this one, the 3 at the end, it means that this one is present. It's read-writable, and it's only accessible from supervisor code, that is kernel code or in zero code. So it's not accessible from user mode code, this memory region that is pointed by this entry. The numbers in black here is the physical address in main memory of the next level in the paging hierarchy. And in memory, we need to know that everything is also stored in little endian, so the byte order is reversed. So the last byte, 63 at the end, is stored first in memory. The next last byte is stored second in memory, and so on. If we take, for example, this entry, it was pointing towards the next level in the paging hierarchy, the page director pointer table. And this one has a page table entry, a page director pointer table, pointed by the virtual address, and it goes on like that until we reach the actual 4 kilobyte page, which is containing the data, and then we can address within that page of the last 12 bits in the virtual address. And it turns out that this specific address has a very special meaning in Windows 7. It's Windows 7's self-referential entry is stored at index 1ED hex, or at index 493 in the table here. And this means that the page directory pointer table that is pointed by the PML4 entry, it points to the same physical address as the PML4 itself. So this means that in effectively all these paging structures, the PML4, page directory pointer table, page directory, page table, and the page containing the data itself is stored in the very same location in memory for this specific entry. And from this follows that if you alter the contents of one of these, you alter the contents of all of these since they are the same. If we look at the fix for Meltdown, what the operating system vendors did, they created a second per process page table to resolve Meltdown. And this second page table, it was reserved for user mode code, and it only contained a very small, very uninteresting kernel stub whose only purpose was to switch back into the old page table that contained the whole kernel whenever you were doing a syscall. And the old page table was kept pretty much as is. Windows decided to keep its self-referential entry in both tables. Linux and macOS employed similar fixes. And what's important to know is that this context switching between the paging tables, it leads to a performance loss, especially on older hardware. So Windows decided to go for an optimization here. Because if you're running a system or admin in Windows, you're already able to load drivers into the kernel by design, and drivers can read kernel memory, and that's really what Meltdown is about. So it's really no idea to protect for Meltdown for admin processes in Windows, since you're already able to read the memory in much more efficient ways. So Windows kept its old way of doing things, the more efficient way for admin processes, and only applied the Meltdown fixes for user mode processes, low privilege processes. Let's also have a look at the PCI memory process file system, which I created the month before I found a total Meltdown. It's a proc-style file system. It's very focused on Windows at the moment, on analyzing Windows stamps. It works really well on Windows 7, 8, and 10 memory. It has some very limited support for other 64-bit operating systems as well. And if you run it with an evil PCI Leech FPGA device that is able to do DMA into a target or victim computer here, you can actually do both reads and writes to process virtual memory via this file system. If you're working with a memory dump, it's read-only. It's really fast. I tried to make it so it intelligently analyzes several gigabytes per second. And it consists of a translation layer that processes virtual memory into physical memory. It does this by first locating the page table base, or the PML4, of the kernel itself. Once it's done this, it's able to map out the kernel virtual memory and hunt for a structure called eProcess, which is a process-specific structure that's actually a linked list. So we can walk this eProcess and enumerate the process names, the PIDs, and more importantly, the page table bases, the PML4s of each process. And once we walk this eProcess, we have a list of processes, and for each process we can create a memory map of the virtual memory by walking the page table, and we can also display the process virtual memory as a virtual file in this file system. I also added in-memory parsing of EXEs and DLLs, and to display them as files and directories in this file system. So let's have a look at it. Let's analyze over 32 gigs in just a few seconds. Let's enumerate processes and load the DLLs, and let's look at the memory map and its virtual memory. So switch over to the demo here. Here I have a memory dump. It's rather big here. It's well over 32 gigs at least. And let's mount it in this file system. It says it's mounted as K here. So let's go into the K. And here I have the actual physical memory of the file I just mounted displayed as a file here. It might not be this useful if you're running it against a file, but if you're running it against a live device on a target, via the FPGA or via the total Meltdown vulnerability, it's quite useful. If you click into the proc folder and sort the processes by name, it tries to enumerate the processes on the fly here. So this is the processes that is running in this memory dump. Let's select a process, for example, the PowerShell process here. And here we display lots of information about the process as files. So you can use your favorite editors editing the files. We can check its name, or we can look at the memory map I just talked about earlier on. And the memory map is, yeah, here it comes. It's actually walking the whole page table here to be able to create this memory map. And here we see the memory regions within the PowerShell, if it's readable, read-only, read-write, or even read-write-execute maybe. And if you scroll down a bit, we see the PowerShell.exe here, and it's where the exe is loaded in the memory space of the process. And if you scroll down, we see all the DLLs and things like that loaded as well. And this is fetched from the actual page table itself that the CPU sees. And we can also click into the modules directory. Here we see the different DLLs that's in the process mounted as directories here. And we can do things like checking the export directories, which functions are exported from that DLL by just checking in a file and the addresses where those are found. Can check which functions are imported by this DLL as well. It also displays as files, and like sections and directories and things like that. We can also, let's have a look at the directory here. We'll do like this. And we have one very big file if we check the PowerShell directory here called the vmem. It's actually the virtual memory and it's mounted as a file. So you can use your favorite tool to actually edit the file or copy memory from it, edit memory, and if you hit save, if you're running towards a live device, it will be reflected into that device. Memory that's not existing is all zeros, so that's kind of uninteresting. But if we remember the memory map, we can see the PowerShell.exe, the base of the PowerShell.exe, for example. Let's jump to that one. And we see the MC header here at the bottom, which is the PE header for the PowerShell.exe when it's loaded into memory. And it looks something like that. We have the different sections and so on here. And then if you scroll down a bit, here comes the code for the PowerShell.exe process. So finding total meltdown, it was just a matter of clicking on this memory map, and it was like instantly visible there. And it will turn out that it was mapped into user mode at this specific address that we checked earlier on. But let's run a demo for that one as well to see what was happening here and how I actually located the vulnerability as such. Let's mount the memory of this vulnerable computer that we just took a look at. If we click into K here, the proc folder, names, and we can check the cmd.exe process here, for example. And if we check the memory map, see the read-only section, read-write section. We see that the cmd.exe is loaded here. We see the DLLs. And if you scroll down, we see lots of addresses at the very end. That is read-write-execute. That starts with 4 Fs. And that's addresses that are typically reserved for the kernel. And in my file system, I filtered out the kernel addresses by default for user mode processes. So I was wondering what is going on here. I was like, do I have a bug in my system? And I was like, went for bug hunting, and I didn't find anything. So I installed a clean install of Windows 7, and the issue was still there. So what is going on here? So let's check out that. Go into the cmd.exe process. Let's have a look at that. And we can check the PML4, the base of the paging table itself. It's stored at this address in physical memory. And remember that file that was containing the actual physical memory that I exposed, the live RAM file in the root. We are going to hex dump one full size, one page, the PML4 paging table, and let's do that from that address the PML4 has. And if I remember the little endian, and if it ended with a 3, it was only accessible from supervisor code or kernel code, and if it was put as a 7, it was accessible from user mode code as well. The lower addresses are like kind of fine. If it's accessible from user mode code, it's how it's supposed to be. But addresses above offset 800 are supposed to be only accessible by the kernel. But if you check this index at 1ED hex or F68, this one, it's the PML4 self-referential entry, and it ends with a 7 if we're adjusting for the little endian stuff here. And that means that it's accessible from user mode, and that's our vulnerability. So I'm going to prepare the next demo a little bit here as well. So the vulnerability was that the Meltdown patch in January, it got one single bit wrong. It should be a 0, bit 0 at this address, but it was a bit 1. So that resulted, if we check the Intel manual, that this PML4 self-referential entry, and in effect the whole paging hierarchy, became accessible from user mode code at a fixed location in virtual memory for every process in the whole system. In order to exploit this one, you don't really need to do any fancy API calls. You can check for its existence by just reading an address. And if it's working, you're vulnerable. If it's not working, if the program crashes, you're not vulnerable. Reading an arbitrary physical memory from an address is a little bit more complex, since you need to select a physical memory address to read from, and you need to manufacture a fake page table entry. For example, something look like this, and you insert it somewhere in the PML4 paging table, which is also the same as the paging table itself. And you need to be careful, so you insert it in a place where there's nothing written before, because if something is there already, there is a chance that the computer will blue screen. But once you put this fake page table entry into the paging hierarchy, you can just calculate the virtual address and that you need to read from in order to read this physical memory. And then it's just a matter of doing a standard memcopy to read whatever physical memory on the computer you wish to read. Or if you wish to write to memory, you do the memcopy the other way around. So the boring stuff for my part, it looked like it was fixed in March. In the March patches, I didn't see these entries in the memory map there. And so I checked the release notes from Microsoft Security. They usually put some acknowledgement on their acknowledgement page and what kind of vulnerabilities they fixed this month. I didn't see anything about this, so it was like kind of strange. So I decided to contact Microsoft Security or MSRC anyway. And they were going to check with their technical department, and they came back just the other day when they checked with their technical department, and I received the green light to publish the blog entry about this one, since it was already fixed. So that's what I did. I published the blog entry and the POC the day after, and kind of immediately Twitter noticed that 2008 R2 was affected as well. It wasn't something that I thought of myself, but it's quite logical, since 2008 R2 is pretty much the server version of Windows 7. And what's a little bit boring here, it was like that the March patches for 2008 R2, they had some quality problems, so sysadmins hadn't been applying the patches for that month. And when I was installing my 2008 R2 and my exploits were still working there. So it was like, ouch, this is not good. And I remember I was contacted on Telegram by Maxime Goriashi from Positive Technologies as well. And it was like, hey, this one is not fixed, it's still working. So I really needed to contact Microsoft Security again. And it seems like they were already aware of this one, that it was still working. And they were working on an out-of-band patch. And they asked me to keep quiet for a day or so while they could get this one out to the public. So just the day after, Microsoft released an out-of-band kernel security update for CV 2018-1038 on March the 29th. So how could I believe that this one was fixed, and how could I miss that it wasn't fixed, and how could Microsoft miss it as well? Let's have a look at the vulnerable virtual machine from March. Let's mount the file system again. Let's check that memory map. Let's check it in the cmd.exe again for simplicity. And if you scroll down to the very bottom here, you see that there are no F addresses at the bottom here, so the issue seems to be fixed, completely fixed, and that's why I thought it was fixed. And but if we try to just dump the memory again, I mean, memory dumping is still working here, so hey, what's going on? This is really strange. So let's check here. And we have the different files here as before, and we check the PML4, stored at this address. And if we check the PML4 paging table, at the index of F68, the self-referential entry, it seems like it's fixed. If you account for the little endian, it ends with a 3, and that means it's present, it's active, it's read-writable, and it's only accessible from supervisor or kernel code. So it seems like it's fixed. So what is going on here? But remember, the fix for Meltdown, for low-privileged user processes, it was to create a second PML4 paging table hierarchy. And if we check the second PML4 for the actual user code, it's stored at a different address from the actual original kernel PML4. And if we check the page table base for the user mode code, we see that index F68 page, the PML4 entry is, we still have that bit set in error. So that's why I completely missed it. It turned out that in March patches, the total Meltdown vulnerability was only fixed if you were running as system or admin. You couldn't exploit this issue. You were unable to run code in the kernel this way then. But if you were running as any low-privileged user process, was still totally vulnerable. To sum everything up, total Meltdown is now fixed. I believe everyone can make mistakes. I certainly did make a mistake, and probably Microsoft as well. But it's super impressive to see that they're able to push out a rather complex kernel security update to hundreds of millions of PCs in less than 2 days. It's like super impressive work from Microsoft's side. And also, I believe that the PCI Leech memory process file system that I demoed here today as well is kind of awesome. You can do other things with it as well. And please have a look at it. And thank you.